my biggest disappointment with all attempts to construct theories of quantum gravity is that none of them, loop quantum gravity, string theory, whatever you name, none of them have been able to address the cosmological constant problem. Right? They usually evade it.
Doesn't string theory address it with supersymmetry?
Well, the point is that in the real world is not supersymmetric in any case. Even if they were supersymmetry, it would be violated at an energy scale of a TeV, and you have the same cosmological constant problem as before, right? So that's the simple answer to that question. The real answer is a bit more involved, but that should do. So there is no way that they address the cosmological constant problem. And therefore, we are missing something really big, right? Every attempt to sort of solve the cosmological constant problem has failed. There are actually now review papers classifying all the different ways people have attempted to solve it, many clever and intricate ways, and they have all failed, which means we are missing something really big. And I like to tell young students they need not worry that all the big problems have been solved and there is nothing for them to do, because we have missed solving the biggest one of them all, right? Now, into this situation, so what happened? Particle physicists realized they could solve the cosmological constant problem, but then it doesn't really affect them. It affects nothing that is done at the LHC. Okay, this is something that only affects stuff on the larger scales, on the scales of the universe. So, as I put it in my essay, it was an accident waiting to happen that when you start making observations of distant objects and you allow for a cosmological constant in your equations, you are going to find it to be non-zero, because you are fitting the data in a very constrained framework where the only unknown quantity in your equation is the cosmological constant. You have matter, you have curvature, and you have the cosmological constant. You can measure the matter independently, you can measure the curvature independently, and you determine the cosmological constant from what's called a sum rule, which is that the fractional energy densities in matter, curvature, and cosmological constant add up to 1. This is a restatement of the Friedmann-Lemaitre equation, which is the workhorse of standard cosmology. And that equation is derived assuming exact isotropy and homogeneity, the so-called Friedmann-Lemaitre-Robertson-Walker metric. And that leads me to answer your second question. So I'm getting there. You asked about evolving dark energy and DAISY. DAISY has got some brilliant data. It's got millions and millions, of 10, 12 million spectroscopic redshift measured with this beautiful instrument they had on this telescope at Kitt Peak. And it covers almost, 35% of the sky by now, right? I think they get to about 40% of the sky eventually. They are still analyzing this data, this beautiful data set. The first equation in their paper is we assume the Friedmann-Lemaitre-Robertson-Walker metric. They assume exact isotropy and homogeneity to analyze their data.
Which is the very thing you're questioning.
Yeah, yes, which I'll come to in a second, why I'm so doubtful about it. But they allow an extra degree of freedom now. They say that it's dark energy, instead of just being something which has got a purely diagonal energy momentum tensor, has got a second term which is proportional to redshift, right? This parameterization is actually without any physical basis whatsoever. It is simply for calculational convenience. It's self-serving. It's so that you can integrate observational quantities like the luminosity distance or the angular diameter distance in a neat way, because it's in the integral. So if you make it proportional to z, then you can integrate over z. It's just that. And then they claim that it differs from zero. They have got evolving dark energy. My question, which I've asked DAISY people several times, is have you checked that your signal that you are actually measuring, like the BAO signal, is it the same in every direction in the sky? I mean, you've got like 12 million data points. Are they implicating a peak at exactly the same position, whichever direction you look over the bit of sky that you have looked at? And I have not had any answer to the question. It is certainly not stated in any of their papers. In other words, they are analyzing the data according to a assumption of a metric that was actually made over 100 years ago. It was in the 1911 paper by Alexander Friedman. He assumed the same metric because at that time we had no data. We didn't even know we lived in a galaxy. right? Lemaitre assumed the same thing, and Friedman and Robertson and Walker then gave the mathematical basis for it, but it was exactly this metric.
So, what is your metric of choice then? Is it LTV?
Well, I don't know. As I said earlier, we can only prove things wrong. It is much harder to find what is right. So, what we have done more recently, and this is something I'm very excited about because this is free of the complications that we discussed earlier about the supernova data and all this technical stuff about stretch corrections, light corrections, progenitor, age dependence, and so on. Messy stuff. People can argue back and forth, and you never get to a consensus. I'm now going to tell you as briefly as I can about something. It's so simple that it was actually proposed 40 years ago. It was proposed in 1983 and published in 84 by George Ellis, who is a well-known relativist from South Africa, and John Baldwin, who was the head of the Bullard Radio Astronomy Lab at Cambridge, at Cavendish Lab, right? And he was undertaking the Cambridge survey of radio sources. And what these guys realized, I was quite intrigued to find that they had actually met at a ex monastery on the island of Crete, where they hold conferences. And this is called the Orthodox Academy of Crete, and they are clearly, I can just imagine them. I've been to that place, chatting, about this thing that Baldwin was about to start counting radio sources over the sky. And Ellis says to him, look, if the microwave background has this dipole anisotropy due to our motion, then shouldn't any distribution of objects on the sky at large distances have the same anisotropy? Because that is arising due to well-known physics. It's arising due to the phenomenon of aberration. So aberration is the phenomenon which that when you are moving, a star will appear to be displaced in the direction of our motion, right? And this was actually, it's a relativistic effect, but it was actually found by an astronomer called Bradley. In fact, he was the professor of astronomy at Oxford over 200 years before Einstein. He actually said that the angle at which you see the star is related to the true angle which the star is at by a formula, which is just a relativistic formula, taking into account that light has finite speed. So Bradley actually worked out to within 1% the speed of light by observing that this aberration was, so many, whatever it was, minutes of arc in the sky, right?
The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new insider feature. It was just launched this month. It gives me a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high quality podcast. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount.
So aberration causes a uniform and isotropic distribution of the sky to be sort of focused in the direction you're moving, right? And you have to also allow for the fact that when you're moving, you see an object at a different frequency than when you are not moving. So if it has a spectrum, you have to allow for the fact that there is going to be different number of objects in that window, etc. So when you do all this, you find that you get a dipole pattern on the sky, which is the same as the CMB dipole. It is V over C. It's a relativistic effect. And V over C is about 10 to the minus 3 because we are moving at a few hundred kilometers per second. In fact, 298 kilometers per second to be precise. And if you do all the maths, then for the case of objects on the sky, like radio sources or quasars, it's actually enhanced a bit. It's about 5 times 10 to the minus 3, right? So what is it? Point 5 10 to the minus 3, 0.5%. Okay, it's a tiny effect. But
Mhm.
to measure something like that, you need at least a million objects on the sky. Now, in 1984, when they published their paper, there weren't a million objects known on the sky.
When they publish Ellis?
Ellis and Baldwin. So they published their paper in Monthly Notices of the Royal Astronomical Society in 1984. But the first sky map of objects, radio sources, that was approaching that kind of a number came out from the Very Large Array in Socorro in New Mexico around the millennium. It was published in, I think, 1998 or 99, right? And this catalog is called NVSS. This had more than a million radio sources, but actually you got to throw a lot of them away because you need uniform seeing over the sky. You are looking for the number of objects above some threshold as you are going in one direction, which will be within your band. So as you are moving, objects which would have been too faint to be seen in your survey
Mhm.
would be boosted above the threshold and oppositely in the reverse direction.
Right.
So you'll see a hot spot and a cold spot. But to do this right, you really need a very controlled survey. You need to have the same sensitivity all over the sky. And when you do counting from a antenna on the ground, as you get closer to the horizon, your sensitivity changes. There are at ionospheric reflection, all kinds of experimental uncertainties enter into the thing. So you got to cut out quite a bit of your data, right? So when you do all that data cutting, etc., you aren't really left with sufficient number of sources. But people did this and they said that we are seeing a dipole. It is in the same direction as we expect, but its amplitude seems to be off. It's a lot higher than it should be, right? So we did this exercise ourselves in 2017. In fact, one of the criticisms was that NVSS sees only the northern sky because from one position on the ground, you can't see the whole sky. You can only see about 40% of the sky, right? But there is another telescope in Molonglo in Australia, which sees the other half. So we combined the two surveys and we made a full sky map. And we saw this dipole, and it was indeed higher than expected. But the same sigma strike again. We did Monte Carlo simulations. We asked how many times would we see something like this by chance, by pure chance, right? And the answer to that question is 2.7 sigma. This effect is not significant at all. It is even less than 3 sigma, right? So, we have to be consistent. We are accusing other people of not having a significant result. The same applies to our result. So we can't claim that it is
Interesting.
significant. So it's a curiosity, but we realize we need better data. And then great fortune struck. We happened to meet up with a astronomer. His name is Nathan Secrist. He's at the Naval Observatory in Washington. And he actually serves on the committee that maintains the reference frame, which is used for satellite navigation. And these guys really need to get everything absolutely right. So they use quasars, which are the most powerful sources in the sky. You can see them out to redshift of a few. They're point sources. They're initially called quasi-stellar sources. That's why they're called quasars. And he had a catalog with, million and a half of these guys, right? Measured all over the sky by a satellite called WISE, which was the infrared satellite, which operated for years and years. We were fortunate to meet up with this astronomer who, in fact, had a catalog of quasars mapped in the infrared. So, quasars are basically supermassive black holes at the centers of galaxies that are gobbling up matter and spewing it out in jets. So basically, this catalog is of objects which are, in fact, quasars are supermassive black holes which are absorbing, accreting matter from around them and shooting them out as sort of beams of plasma. But the ones that we are looking at are in the infrared. So, in fact, they are really the accretion disks around the central black holes, right? Similar objects shoot out these beams and they become radio sources. So, the radio sources and the quasars that we are looking at do have a connection, but the catalog that we are using has got no radio sources in it at all. It's a completely independent catalog, right? I mean, the way that they're cataloged is completely different. So, a different class of objects is picked out in the survey. The quasars that we are looking at have been mapped by this satellite all over the sky. But again, we have to make various quality cuts because we need a map of these quasars on the sky, which gives us how many quasars there are per unit pixel on the sky. And we have to make sure that this is not affected by something mundane like the ability to tell them apart when they're very close to each other. We don't want to count two as one, for example, or we
Yes.
don't want to be somewhere where there is absorption and the number is diminished because of that. So these are the kind of things that astronomers have to deal with, and they have developed various methods to check for these things. And our colleague Nathan is an expert on these. He is totally meticulous about looking for systematics, which is, again and again, that's what comes to bite you on the ass when you think you have a result. You have to be very, very cautious. But let me just summarize the situation by saying that we have convinced ourselves that what we see is indeed a dipole on the sky. And that dipole is twice as large as the dipole in the cosmic microwave background, right? What that means is that normally, since we believe that the cosmic microwave background dipole is the result of our local motion, the idea is that if I do a Lorentz boost at 369.8 kilometers per second, in that frame, I would then see the microwave background as isotropic. The dipole would disappear. Okay. Because the dipole is simply because I'm moving with respect to the frame in which everything is isotropic.
Right.
And the implicit assumption has always been that in that frame, the distribution of matter is also isotropic.
Okay, so right now you're distinguishing between a kinematical dipole and a matter dipole?
Yeah, so I'm saying the matter dipole should also be kinematical in the standard model, that the dipole that we see in the matter should be exactly due to the same reason that we are seeing a dipole in the radiation, because the two were connected together in the early universe, then they decoupled, right? But the last scattering surface of the cosmic microwave background that we see looks pretty isotropic, apart from little fluctuations, right? And then we see this huge dipole, but we say, well, that's nothing to do with the early universe. That's to do with just our local motion, right? And by the same token, if we do this boost, we apply this boost to all the things that we measure about matter, namely the redshifts, the luminosity distances, then the hope is that we will have corrected for our local motion, and we can then analyze the data according to the Friedman-Lemaitre equations and, deduce dark energy, deduce devolving dark energy, whatever, the usual machinery. But now I'm saying that there is a huge sort of, spoke in the wheel. It turns out that that whole procedure that is followed as standard, including by the DAISY collaboration, is now subject to question, because we finding that the dipole in the matter is not the same as the dipole in the CMB. That is the necessary requirement for the standard procedure to go through, right? So let me step back one and just describe it in a few short sentences. Let's say the universe is on large scales homogeneous and isotropic as we want it to be or take it to be in the standard model. In reality, we look out and we see, yes, the cosmic microwave background looks pretty isotropic. That supports what I always thought. Except that there is a huge dipole 100 times bigger than the other little fluctuations, which are negligibly small. They're 1 part in 10 to the 5. What is this dipole? And then somebody says, oh, no, that we understand. That's just due to our local kinematic motion. We just need to correct for it. And then we are back in the reference frame where everything is really isotropic and we can business as usual.
Uh-huh.
We can use the same model that was invented over 100 years ago by Alexander Friedman that still works. Great, right?
Yeah.
And we carry on. That's what DAISY are doing. That's what DES are doing. That's what every collaboration is doing. They're using the same equations that were written down by Friedman and Lemaitre nearly 100 years ago. Okay. I'm saying that to date, it has been okay to do that because there was no reason to believe otherwise. But just in the last few years, we have got the data that allows us to do a consistency check of whether the metric of the universe is indeed Friedman, Lemaitre, Robertson, Walker. That is the Ellis-Baldwin test. To do the Ellis-Baldwin test, which is simplicity itself, it's just special relativity. It's just saying, if you see a dipole in the cosmic background due to a local motion, you should see the same dipole in the sky distribution of cosmologically distant sources. And when we do that test, we find that yes, there is a dipole in the distribution of distant sources like quasars and radio sources, but its amplitude does not match. Its amplitude is not what it should be. And that has been now established at more than 5 sigma by multiple data sets, radio data, quasar data, data taken from the ground, data taken from a satellite, data analyzed by 3 independent groups. We are all getting the same answer. It's significant. So in a recent review in Reviews of Modern Physics, we have given a detailed description of these different data sets. We have discussed all the possible systematic uncertainties that people are quite rightly concerned about. And we show that to date, there are no showstoppers. There is no reason to believe that this result is not correct.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.